disappear. Just leave it on that chair. All right. Could we settle down, please? Thank you. A bunch of announcements. First, the homework should be handed into that chair over there, so I can pick it up. The second announcement, a bunch of you have periodically asked me whether CVN would have the tapes of this course available. So I talked to CVN and they assure me that the tapes will be available. I'm not sure when. I'm hoping that they would be available before the weekend. And if CVN folks are listening, this is just a hint. Yeah, it's going to be on. When it's going to be available, it's going to be online. So the question was whether the tapes will be available as physical tapes or online. If it's available, it will be online streaming. So you should be able to view it from wherever you are. Could we settle down, please? You can turn it in at the end of class. That's all right. What else? Do I have any other announcement to make? Oh, there is a homework that will be assigned today. So there will be a homework due on the day that you have the midterm. I'm sorry, it's just I have to make sure that you understand what's due for the midterm. So there will be a homework that will be due that day. We'll make sure that in order to make sure that you have the solutions, I want you to submit the homework in the first session so that I can immediately give you the solutions and you have at least a gap to work with. The TA would try to go over everything that's in the homework in his recitation sessions with different examples so that you get what's happening. All right. So now I just want to give another example of the absolute value type constraints that we talked about in the morning, and then we'll go over to asset pricing. So the story here is that there are three time points in this particular example. There was a time point somewhere in the past, let's call it -1. There's a time point here, that's today at time 0, and then there is a future time 1. So at this point, this investor bought a portfolio of, say, N stocks. So his portfolio was S1 up through Sn, which is the number of assets, number of shares of each stock that he bought sometime in the past. And the price that he paid for this was Q1 up through Qn. Now this investor is sitting at time 0, and what he wants to do is liquidate some of his position in order to get K dollars. So he needs K dollars here. The present price of these securities is a vector P, P1 through Pn. And he wants to liquidate the portfolio in such a way that his future expected value at the future point is maximized. And the future expected prices is the vector R, which is R1 through Rn. The other issue is at this point he has to pay a transaction cost at the rate of alpha. So the alpha per dollar traded. It doesn't really matter whether he buys or sells. For the amount traded that he has to pay a certain fraction alpha of that as a transaction cost. And if he does liquidate some position, he pays capital gains tax of beta times the difference. So if he sells, let's say, beta per dollar or per positive change in price. I'll just make it clear in a moment when you do the modeling. And the question now he wants to decide is how much of his initial portfolio S this person needs to liquidate in order to make sure that he gets K dollars at this point and maximizes his future expected value of the portfolio. And what we are going to use is the decision variable is the new portfolio. And this new portfolio phi has also n components, phi1 up through phi n. And therefore, the objective value of this person is very clear. It's max sum of I going from 1 through n of Ri phi I. Phi I is the number of shares of the particular assets that he decides to move to today. Future prices are this, and therefore that's the future expected value of the portfolio. And the only constraint this person has is that it needs to raise K dollars in cash today. So what is the constraint? How would we formulate the constraint here? So here's what the formulation of the constraint is. He comes into time 0 with an initial wealth of the current prices, Pi, Si, I going from 1 through n. This is the current, this one is the total wealth that he enters this particular time unit with. This is the new wealth that he has in his portfolio. So here, minus sum I going from 1 through n, Pi, phi I. This is the wealth that he still has in its portfolio. Phi I is the new portfolio, Pi times phi I is the total wealth that he's got in asset I. Sum that up, that's the total wealth that he's got right now, which he takes over to time 1. From the old wealth, you have to subtract the new wealth, you have to subtract the transaction cost. And what is the transaction cost? It's minus alpha times the total dollar traded. And what is the total dollar traded? I going from 1 through n, the price of the ith asset, times the change that happened in the ith position. Right, so that's the transaction cost. And we are just assuming a straight proportional transaction cost. You do not pay any fixed cost for doing this transaction. What's the next term? The next term tells you the total amount that he has to pay as capital gains. So the capital gains tax is paid only if, that's a typo over there, that should have been QI. So let's subtract, there's a minus sum I going from 1 through n of Pi phi I. The capital gains tax is at the rate beta, but you pay the capital gain tax only if you made a profit. That means Pi minus Qi is positive. So if this is a typo, this should have been Qi. So if Pi minus Qi is positive, which means the current price is higher than the price that you paid for, then you pay capital gains, otherwise you don't pay capital gains. If you made a loss, you don't pay any capital gains on it. And you pay capital gains only if the current position is less than the position that you were holding before. If the current position is less than what you were holding before, it means you sold that stock. So you made some money off of that stock, and therefore you pay capital gains on it. So this times Si minus phi I, positive part. So Si minus phi I is positive, means that this positive part operator means that if this is positive, it take the value, otherwise you take it 0. Any questions? So this is the problem that we want to solve. Phi is unrestricted. And now what we want to do is reformulate that as a linear program. So again, we could use the trick that we used in the morning. What we did was anytime we wanted to remove a nonlinear operator like this one or that one, we introduced 2 new variables. So we can do that trick. We can put in a variable ui, which is going to represent phi I minus si positive part. So I'm going to write phi I, which way do I want it? I actually wanted si minus phi I, so might as well write it that way. Si minus phi I is equal to ui minus vi, and the absolute value of si minus phi I is equal to ui plus vi. Ui and vi are non-negative. This is what we did in the morning. We introduced 2 new variables, 2 non-negative variables. The sum of those variables is equal to the absolute value, and the difference of the 2 variables is equal to the quantity itself. And to linearize this problem, I replace this absolute value by the summation here, ui plus vi. This positive part I know is going to be represented by the variable ui itself. So this becomes just ui. This si minus phi, I'm going to put it together, so I don't have to worry about this, but I know si minus phi is ui minus vi. So this becomes the sum of I going from 1 through n pi of ui minus vi. The only reason I wanted to go through this example is that in this example, for the first time, you see using just the variable ui instead of looking at variables. Typically, in the formulations, you either use the value itself or you use the absolute value. But sometimes in modeling these kind of trading examples, you end up using only one part of it, the positive part. So here I just use the value ui. Up there, I just replace phi in terms of the new variable. So this becomes si minus ui plus vi. And then put in the constraints that ui, vi are greater than or equal to 0 for all I. Right? So that becomes a linear program. Again, there is at the bottom of this, there is a question asked whether this will work all the time. You have to be careful about that. So you define these variables and you end up getting this problem. The question is, what happened to my constraint? All of this has to be greater than or equal to k, the total money that I need to generate right now. So you have to keep in mind that this trick of replacing absolute values by these two variables doesn't work all the time. The same problem that we had in the morning when we were trying to see that max or absolute value is less than or equal to v can be linearized, and absolute value greater than or equal to v cannot be linearized. Whether you introduce new variables or not, the same problem remains. So you have to be careful while formulating this problem as to whether it's going to work or not. You probably would get some idea of whether it's going to work or not, but on Tuesday we're going to start talking about nonlinear programs, and we're going to start off by defining things like convexity. So if the problem is convex, which you don't know yet, many of you probably know what a convex problem is. If you don't, we'll talk about it on Tuesday. If the problem is convex, this trick is going to work. If the problem is not convex, it's not going to work. Questions?
Again, how do you substitute in the ui minus vi in that equation?
This one up here? Right here? Okay. So there was this term here.
Isn't that si over there?
Yeah. So there were two terms.
And where's the
So yeah, that's what those two terms I combined. So here was the constraint in terms of the old variables. There is this term sitting on the corner here, which is pi si, and then there is this term over here, which is pi phi. I put them all together and then replaced it by ui minus vi. Any other questions?
So there's still a positive on pi minus ui.
Where? Yeah, so that's a constant. Those are numbers. That's the pi is the present price. I know what that data is. Qi is the old price. I know what the data is. That's not a decision variable. So I don't care about it. It's some number that I just stick in there. So I have to worry about making sure that the variables don't have a positive part operator sitting on top. But if the constant, this should have been Qi. So, but if the constant has it, doesn't matter. All right. So now we're going to change. So in terms of the models, this is where the models end. In the homework, I haven't yet assigned it. I will assign it at the end of the class, figuring out how far we go in the class today. In the homework, you will get more models to look at. Ali would also cover more models in his recitations. But in terms of the LP models that people come across, this is about the range. What did we cover? We talked about the beer ale example, where you had a raw material and you wanted to allocate them to maximize profit. Then we talked about the bond example today, where you had a certain requirement and you had a bunch of things that you could invest in to meet a certain requirement. The oil trading example was the same thing. You had the requirement that you had to meet a certain fuel's characteristics, and you wanted to mix some fuels to get that characteristic. So those are sort of standard, typical models. The other kind of LP model that show up is this time-phased model, where decisions happen over time. Although the bond model had decisions over time, they were almost artificial. It wasn't necessary. All the decision was made at time 0. But the short-term cash management example was the case where things happen over time, which are network models. Maybe I'll give you an example, a homework problem on inventory control, which will also give you an example of this time phase thing. Different things are produced at different times. They have to be stored and then taken forward and so on. And then the last model that we talked about were these linearizable models. There are two kinds of linearizable models. One is this one, where you have quantities like absolute values, quantities like positive part operators show up. The other kind of model that we talked about in the morning briefly are things of this sort. They are related. It's the max of a bunch of linear functions, and you want to minimize them. Or the other thing is that this max of a bunch of linear functions has to be less than some other number C. Even if you had this problem, you convert it into that problem anyway. So this is sort of the prototypical linearizable model. Question?
Why that's UI?
What's UI? This part. Okay. So this is that term that we are trying to replace. So Si minus phi is the variable that I want to replace by something linear. And in the morning, we were talking about this kind of formulation, that the way this new variables show up is because I can write the absolute value of any number x to be equal to its positive part plus its negative part. So let me give you an example so that it becomes a little clearer. Suppose the value of x is equal to minus 3.5. Then I define the positive part of x to be the maximum of x and 0, and in this case it turns out to be 0. Maximum of minus 3.5 and 0 is 0. The negative part is defined to be the maximum of minus x and 0. So that turns out to be 3.5. Minus of x is minus 3.5. The max of 3.5 and 0 is 3.5. Now the value of x can be written as x plus minus x minus, which checks out because that's 0 minus 3.5. It becomes minus 3.5. And the absolute value of x is written as x plus plus x minus, which turns out to be 3.5, which is exactly the same thing that you would expect if you take the absolute value of x. So when you represent them, this variable that is positive in both of these expressions plays the role of the positive part of the variable. This variable, which is positive in the absolute value expression but negative in the real value expression, plays the role of the negative part of the variable. So what we want to do, and here's the expression, I'm replacing Si minus phi by Ui minus Vi, and the absolute value of Si minus phi by Ui plus Vi. So this variable Ui that I have here, if you compare it with this example here, plays the role of the positive part of Si minus phi. And that's why over here, I want to replace Si minus phi positive part, so I replace that by Ui. Okay? If it had been the negative part, then I would have just picked up and put the value Vi over there. It's just pattern matching from what this looks like and what this is. Any other questions? Okay. So now we are going to change gears and actually try to use linear programming in proving the existence of state prices. And I don't, what time do I have? 2:18, good. I should be able to do it. So here's the story. We're going to look at a single period model, a single period finite state market model. And then I don't think I'll have the time today to expand it to multiple stages, and I'm not even sure whether I'll do it in this course. but at least you will see it in FE1. So here's the story. The world is in some state 0 today. Here's time 0, that's today. Here's time 1. At time 1, the market closes, everything is over. The game is over. We don't have multiple days in this. At time 1, the market could be in one of m possible states. State 1 up to state m. And there are certain probabilities associated with them, say P1 through Pm. And the reason, if you look through the notes, the probabilities don't play a role at all, is the only thing we require is that they be strictly positive. Any probability that's strictly positive, let's just worry about what happens in that case. So by strictly positive probability, all I mean is that m possible states are there. I just don't know what their probabilities are. I don't really care about it. But it's not 0, which means that each of these states does happen. Now, at both of these time periods, I have n securities available for trading. So there are m states. So let me just circle these things, if you can see it from back there. There are m states, and there are n securities. The same securities are available in both time periods. I'm getting crazy now with all these colors. Okay. So let's give some examples. Say m was equal to 4. If m was equal to 4 and n was equal to 3, then you would have some prices here. Let's say these 3 securities are available at 2, 4, 3.5. And of the 4 states that we have here, their prices are given. These numbers might be totally garbage. So in every state of the world, there is a 3 vector that's given, which gives me the prices of the 3 assets that I have. All right? So that's the vector in my notation over there. This vector stands for S omega 1. This vector is S omega 2. This vector is S omega 3. S omega 4. So that's the notation that I'll be using. And this vector over here is the vector S0. The price in the 0th state, in the state that's today. Okay? At time 1, for every state there is a vector. All right? Now what I'm going to do is buy a portfolio of these securities at time 0 and hold them up to time 1. And the whole game that we are going to play in this rest of this lecture is about what can we say about this trading process, buying something here and liquidating them here just to get dollars. That's the entire story. So let's say that there is a position vector theta, which has now 3 components, theta 1, theta 2, theta 3, that I start with at time 0. The value of buying this, or the cost of this portfolio, is going to be the vector S0 transpose theta. Right? It's just take the first component, multiply by theta 1, second component theta 2, third component theta 3, and add them up. In each of these states, the payoff would be S of omega 1 transpose theta, S of omega 2 transpose theta, S of omega 3 transpose theta, and S of omega 4 transpose theta. All right, those are the payoffs that I get at time 1 from holding this. It will be convenient for me to think of the payoff as a vector. One payoff value, so all of this is a scalar value for the first state, a scalar value for the second state, and so on. Now I'm going to create a payoff vector which has one component for every state. So the payoff vector, what notation did I use over there? Probably didn't have any notation. Ah, it's there. Okay. So the payoff vector is going to be what? Let's call it y of theta. The payoff that I get from holding a portfolio theta is simply this thing. S omega 1 transpose, S omega 2 transpose, S omega 3 transpose, S omega 4 transpose, whole thing multiplying the vector theta. I just stacked up the 4 components together as a vector. All right? This whole thing can be written as this matrix transpose. S omega 1, S omega 2, S omega 4, the whole matrix transpose theta. Okay? The reason I'm going through this is because we're going to play with these matrices over and over again, so I want you to remember what this payoff matrices look like. This whole matrix will be called S1. Just like this matrix is called S0. Question?
Can you explain the transaction process itself as to what happened between 0 and 1?
Nothing. The market opens at time 0, you buy theta, market closed down. You can't do anything. At time 1, the market opens again. It will be in one of these m possible states, and all you can do is liquidate your portfolio and get your money. That's all you can do it. There's nothing else. So in between time 0 and time 1, there is nothing possible. Later on, which will not happen in this class, which will happen next semester, what we will do is have more time spots. So it will be a discrete time market. Right now it's a single period market. So at this point, all I'm trying to see is that if you had to commit yourself to a portfolio now for something that you see at time 1, what happens? Okay?
So I couldn't get the last operation.
Okay. So what I did was that I computed the value of this portfolio at each of these 4 possible states, stacked them up as a vector, and now all I did was I said, well, this looks like a transpose, 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 put it all into a big vector, take a transpose of that matrix, that's exactly this matrix. So all I'm writing is y of theta in a different form. It's just doing matrix manipulations. So the thing that I want you to remember is that, and this is what we'll need in a moment, is that this matrix S1, how many columns does it have? Let's not talk about 4, let's talk about M and N. How many columns? M columns. So there are M columns, 1 for every state, and how many rows? How many rows for each of them? N. So there is it's M times N. Oh, what am I doing? I'm writing it the other way around. Sorry. It's the number of rows is, what was the color I used? M. So the number of rows is N, and the number of columns is M. 1 column for every state of the world. And the column basically lists out the prices of all the securities in that state of the world. Okay? That's what the matrix S1 looks like. It's got a column for every state of the world, and that column lists out the prices. Okay. So that's sort of the mechanism of how this market is going to. If I have to describe this market, what do I have to do? I have to tell you the vector S0 and the matrix S1. If I tell you the vector S0 and the matrix S1, you can tell me anything that happens in this matrix, in this market. There is nothing else you need to know. You might want to worry about probabilities. If you're looking at expected values, you might need to know the probabilities, but that's not something that we'll concern ourselves with right now. Is this mechanism clear? Is this notation clear to everyone? There is something missing here. Stop me, because a lot of manipulations will be done with the vector, with these S0s and S1, and I want to make sure that you understand how these things have been created.
Before the transpose. I think it's
Yes, the S1 matrix. So this matrix down here is the S1 matrix. So the payoff actually, it's a good point. Let me make it clear. Let's redefine it. So S1 is S omega 1, S omega 2, and so on up through S omega m. And take its transpose to get the payoff vector. Anything else? Okay. So now I have to introduce a bunch of different notations. for this market. So we'll call a security, so we are given some n securities here, some n basic securities which describe the market. And the way I'm going to describe the market is by giving you S0 and S1. Now comes another security. And what is a security? A security is simply described by its price at time 0 and its payoff at time 1. In this market, that's all that can be done. We will call a payoff, a security with payoff X, attainable if it can be written in this form. Actually, there's a transpose missing there. This should have been S1 transpose. So I'm going to remove out these examples from here. And I'm going to leave just the matrix S1 sitting here. So what the first thing says is that X attainable means that X is equal to S1 transpose theta for some theta. So what is X? X is a vector X is a vector in Rm. It represents payoff tomorrow or payoff at time t in all states of the world. So X sub I would be the payoff in state I. All right? So this notation says if X is attainable, it means that I can construct a portfolio at time 0 whose payoff is exactly equal to the payoff that I get from this security X. That's the definition of attainable. I can find the portfolio at time 0 such that if I look at the portfolio's payoff, which is S1 transpose theta, that's exactly equal to the payoff that I get from that security X. A market, this market, is supposed to be, is called complete if all payoffs are attainable. If everything, no matter which vector X you give me in Rm, I can find you a theta such that S1 transpose theta is equal to X. All right? So that means that S1 has at least rank M. It can't have more than that because one of the dimensions is M. Typically, it could be N if N is less than M. Okay. Now, so far, so this notion is that of replication. I mean, we haven't used the word replication, but it basically means that the payoff of the security X can be completely reconstructed by looking at a portfolio theta. Theta and X must be exchangeable. If you have X and I give you theta, you should have no trouble exchanging them. They're basically the same thing. Market is complete, meaning any portfolio, any X that you give me, I can replicate it for you. I can give you a theta whose payoff is exactly equal to X. The next notation is different from securities. We'll call a strictly positive pi a state price vector. So pi is a vector in Rm. It's a value that you attach to each of the states. So let's not worry about the probabilities. That's not something we'll care about. But pi 1 up through pi m, we want them strictly positive. So none of the components can be 0. So a vector of m components is called a state price vector if the price of any attainable security, so suppose X is an attainable security, then its price today is given by pi I times xi summed over I going from 1 through m. And that's why this thing pi I is called a state price. Xi is the payoff in state I. Pi I is the value of that payoff. If you add them up, you get the price that you have to pay today. So somewhere in there is also buried an interest rate that we don't really care about right now. Question?
What's the difference between value and price?
Well, good question. Really, nothing. That's what we are going to ultimately try to prove, that this is inequality. But Right, for now, what I'm saying is the payoff happens at time 1, and you get only one of these m possible payoffs. You don't get all of them. The world tomorrow can be in one of the possible states, and you get the payoff associated with that state. If the ith state appears, you get xi. If the mth state appears, you get xm. The price is what you pay here. Price you pay today for something that you get tomorrow. And we're going to say that a vector pi with m components is a state price deflator, or was it what did I call it? State price vector, if it so happens that for any security x that can be replicated, that I can write in this form, the price for that security that I pay here is exactly equal to this expected value in some sense. Except the pi's don't have to sum to 1. So it's not a probability vector, it's just a vector of positive components such that the price that I have to pay at time 0 is as if I'm taking the expected value of the payoff that I get tomorrow. But not quite the expected value because they don't all sum to 1. Question?
Does that mean the summation over there you said from 1 to m?
Yes.
Does that mean there's only one term that's non-zero and all the others are 0? Because you said there's only one state that's possible for
Two things. X is a vector, right?
Yeah.
X is a vector with m components. Our notion says that if state I appears, xi is the value that I get. This is just an algebraic expression. I know the entire vector. I multiply them with pi i's. There's nothing about which state has appeared here, nothing at all. They're just two vectors. There's an x vector, there's a pi vector. I take their inner product. Okay, question?
Our common notion of the price today is as it's the body center of future payoffs with the coefficient being the probability. Why don't they sum to 1?
Well, because of interest rates.
Oh,
Because, there is a,
yes.
so they may not sum to 1. Okay? Question back there? Yeah.
When you say payoffs, do you include dividends or just the capital gains or losses?
Well, my market just finishes there. Nothing
Because
happens.
there are models that calculate the fair price of the stock using the dividends.
Yes, but in those models, typically you'll have to have multiple periods happening. So here, my market just closes at time 1. It just opens at time 0, closes at time 1. You want to include the dividends as, it doesn't really matter. It's all immaterial. So the question asked back there was, what do I mean by payoff? Do I include dividends or do I just include the value of the share and whatnot? So here what happens is that after time 1, it's worthless paper. You better get all your money at time 1. And that includes dividends, that includes share prices, whatever it is that they're willing to give. If the owner of the company wants to give you a free gift, that's a payoff. It's just over. Question?
Could you please explain that equation one more time in those financial terms?
This one?
Yeah.
Okay. So far we have not attached any financial meaning to the vector pi. I'm simply saying that I will call any vector pi which has the following property. It must be strictly positive for every component, and it must have this property that if there is a security x which is attainable, meaning that I can replicate it, then the price at time 0 for that security is exactly given by this expression. For any possible x, this is for all x attainable. So I'm not allowed to choose the pi. So the thing that's very important is that I'm not allowed to choose a different pi for different x's. Of course, I can always make this thing happen if I'm allowed to choose a pi for every different x. There's a fixed pi which prices all x's all at the same time correctly. Okay? Any other questions about this notation? Okay. We'll use another quantity called a numeraire, which is going to be the story. A security which has a strictly positive price can be used to normalize the prices of all other securities. I can start quoting the price of different securities in terms of a security which has a strictly positive price. Why do I want to do that? Well, that removes units from the game. I mean, these securities could be listed in dollars and francs and whatever. I guess francs don't exist anymore. Euros. So by dividing by a particular strictly positive, a security with the strictly positive price, the units are gone from the game. I can just talk about ratios. Ratios are pure numbers. I don't have to worry about changing anything. For now, this is not really important. We'll come to it when we want to do something with the state price vector. Just think of it as normalizing the stock prices in terms of one particular asset that never goes bankrupt. It never goes to zero. Okay? All right. We'll need, so in this whole story, the rest of the class is about using arbitrage to show the existence of a particular pie. And if there is no arbitrage in this market, then there must exist a state price vector. And that state price vector actually gives us a probability measure if you put a numeraire on it. So what is arbitrage? We have been sort of talking about arbitrage quite a bit in this class without actually defining it. So we'll define two kinds of arbitrage, both of which are important. So type A arbitrage means that there exists a portfolio theta such that, what did I do here? Okay, that's fine. So S0 transpose theta negative means that you're not paying for that, but you're being paid for taking this portfolio. So theta costs negative amounts, and that's a payoff at time 0, but it has non-negative payoffs in all states of the world tomorrow. So you get some money at time 0, and you don't lose anything at time 1. Okay, so that's one kind of arbitrage. This is the kind of arbitrage that we have been looking at in the bond problem too. We're making profit right now, subject to non-negative payoffs tomorrow. The other kind of payoff, again a transpose is missing, is the following. You make a non-positive payoff right now. It could be 0. You may get no money right now. You make non-negative profit tomorrow with the proviso that S1 transpose, there should be a transpose here, S1 transpose theta is not 0. So one component is strictly positive. So vector S transpose theta, this is the payoff vector associated with the portfolio theta is non-negative, but not 0. And the payoff of this theta, or the cost of this theta right now, is non-positive. So both of these are plausible definitions of arbitrage. First one says you get a payoff right now with nothing in the future. The second one says you may not get anything right now, but with a positive probability you'll get something positive in the future. All right? The way we are going to, I mean, are these two definitions clear?
Does it mean that it will be positive in that period almost everywhere?
No. It could be 0. It's not almost everywhere. But it's...
In probability measure terms, it should be with probability 1 that it will be...
It's not with probability 1. With probability greater than 0, strictly greater than 0, you'll make money. With probability 1, you're non-negative. But with probability strictly positive, you will make money. Okay? So we're not guaranteeing. In this case, we are guaranteeing that the probability 1, you're non-negative, and probability 1, you make money today. Or there's no probability required. A certainty you make money today. In this one, you're simply saying that there is a positive probability of making money.
There's a state where you...
There's a state where you make money. In the discrete case, it just means there's a state that you make money. If it has a continuous thing, then you don't have a notion of a state, then you have to talk about probabilities. Okay? And now the whole game that we're going to try to prove is that if both of these kinds of arbitrage do not exist, then you can prove the existence of a state price deflator pi, meaning that everything in this market can simply be priced by knowing what the payoffs are. As soon as you know the payoff, what happens here, you know a price at time 0.
This is like saying that you have a risk-free, risk-neutral probability. It's like,
Assuming that you have a numeraire.
yes.
If you add on top of state price vector a numeraire, then you get a risk-neutral probability. Okay, so let's work through that, and all of that is just going to be done through duality. And what we're going to do is introduce some more notation, which is going to cause some problems. Okay, which is not very good. Okay, there is There is some other transposes missing which I'll fix. So let's keep all of this story. So what I'm doing next is I'm producing for you. I basically want to translate the two word notions of arbitrage. Here are the two definitions of arbitrage in words. And I want to transform that into a simple statement in terms of the portfolio. One matrix, what happens to it? So what I'm doing is I'm going to construct a matrix A. And what this matrix is going to do is there is a negative sign missing, which on the left-hand side. It's going to put the S1 transpose up here. So S1 transpose tells you the payoffs at time 1 and minus S0 transpose at the bottom. This is the payoff at time 0. Okay? Now suppose I look at a portfolio and look at this quantity, A times theta. So theta is a portfolio of assets that I choose here. So theta lives in Rn. It's the positions that I hold in the n securities that are available to me. If I look at this matrix multiplication A theta, what does that give me? It gives me S1 transpose theta in the top components minus S0 transpose theta in the bottom component. I just multiplied it throughout. Okay? So the top part here, this part is the payoff at time 1. And the bottom here is the payoff, not the cost now, but payoff at time 0. So the first statement over there says that if there is no type A arbitrage, that means that there does not exist a theta such that A theta is greater than or equal to EM plus 1. What is EM plus 1? It's the basis vector with zeros in the first M components. Remember, S1 transpose theta is the payoff vector at time 1, which means that this quantity up there has M components. It simply says that you cannot find a theta such that this happens. Right? So what am I using here? I'm using simply the fact that my definition of type A arbitrage says that there exists a theta where S0 theta is less than 0 and S1 transpose theta is greater than or equal to 0. If there exists something like this, I can always rescale that theta such that the money that you make here is exactly equal to minus 1. Right? Because I'm saying this is strictly negative and that's non-negative. Just scale it so that the money that you're making at time 0 is strictly minus 1. That's what's going on here. Or strictly greater than or equal to minus 1. That's what I'm saying. So this is an equivalent statement to saying that there does not exist any arbitrage of type A. Is this manipulation clear to everyone? What's happening over here? All I did was I took the same word statement and stuck them, made a new matrix A and put it all together so that life becomes a little convenient. All right? Okay. What about type B arbitrage? Well, it turns out that all of that statements can be made with this A matrix in one shot. There is no type B arbitrage if and only if there does not exist theta such that A theta is greater than or equal to EI. Instead of EM plus 1, you now have EI. What's happening with EI? That's a vector which has zeros everywhere except the ith state where it has 1, zeros, and 0. So this is the ith state. Again the same argument. Type B arbitrage with positive profit in the ith state simply says that there exists a portfolio which doesn't cost anything right now, which is S0 transpose theta is greater than or equal to 0. It has non-negative payoffs in all states of the world except in one state of the world where it's a strictly positive payoff. Again, I can do a scaling so that it makes sure that the payoff in that state is greater than or equal to 1. Okay? What does all of this mean? So in order to use duality, I'm going to construct an LP which looks like this. I'm going to maximize 0 transpose theta. So my objective vector is 0, subject to the constraint that A theta is greater than or equal to EI. And theta is free. I can choose any theta I want. Question?
What's the dimension for EI?
Which one? M plus 1.
M plus 1.
M, S1 transpose has M.
Right, but there's no notation to indicate that EI's dimension.
Well,
Right.
you can make sense of the fact that if I'm taking A theta and I have to compare it with EI, you better make sure what the dimensions are.
And it's for all I from running through
M.
from here.
Yes.
For all I.
For all I. Any I you pick. For all I from 1 through M, this must hold. And that one is picked up as M plus 1. Okay? All right. So this is the... So what does this LP try to do on the left-hand side? Here, all I'm saying is I want to find an arbitrage opportunity. That's all I'm doing on the left-hand side. Question?
Can you please explain that A theta part? I didn't understand.
Okay. So A is an artificial matrix that I've created. And I want to just think of A as the payoff tomorrow and payoff today. That's what this is doing. So payoff tomorrow is S1 transpose. If I take a portfolio theta and I construct A theta, S1 transpose theta would tell me the payoff tomorrow. The cost of it is S0 transpose theta, but I want to think in terms of payoffs. So the payoff today is minus S0 transpose theta. Okay? So that's what it's sitting at the bottom. So the whole idea here is that arbitrage talks about non-negative payoffs. Non-negative payoff today, non-negative payoff tomorrow. And therefore it's more convenient to think in terms of this matrix A, which has everything together, rather than having two different ones, one with S1, one with S0. So all I'm saying is that the same information that existed in S1 and S0, I can stack it up in this matrix A, and computing becomes a little easier. All the story can be told in terms of S1 and S0 separately. It just makes algebraically easier to do it here. I can do everything in one sort of collected sense. Like no arbitrage now means A theta is great. There does not exist a theta such that A theta is greater than or equal to EI for I taking values from 1 through M plus 1. It's a standard statement. But if you look at the earlier statement in terms of the arbitrage, here it appears that there is something not quite symmetric about these statements. A and B are not quite symmetric statements. By putting A, it all becomes together as one. Okay. So now what I'm going to do is I'm trying to find an arbitrage opportunity. I know it doesn't exist, or I'm assuming that in the market there is no arbitrage opportunity. So I'm trying to look, let's not worry about the objective value. It's anyway junk. At the bottom, all I'm saying is find me a theta which is an arbitrage opportunity looking at the ith state. All right? The top says 0 transpose theta. So any feasible solution to this LP will be an optimum solution. So optimality is not of concern to us. Only thing we care about is feasibility. Whether there is a theta which makes it feasible. I take its dual, and the dual looks like this. Max of yi, yi, because it's coming from the ith component of the basis vector ei, such that y is non-negative. That's coming because this is a non-negative constraint, and A transpose y is equal to 0. What did I do? So it should have been, yeah, well, okay. I did two steps all at the same time here. What happened was that this is a bizarre constraint, and therefore its dual variable has to be non-negative. Non-positive. So y had to be non-positive with A transpose y equal to 0, and I had to minimize yi. So I just take everything the sign opposite and maximize yi. So it's just two steps along the way, but it's basically the same dual. It's nothing different has happened. Okay. But perhaps actually let's do it that way. It makes life a little simpler. Well, okay. The answers that I want will be the same whether you do it the other way or this way. So the primal here is infeasible. Because by assumption, there is no arbitrage in the market, therefore the primal is infeasible. When the primal is infeasible, it means that it does not have a finite objective value. It's minus in this particular case, since it's a maximization problem, its value is minus infinity by definition. But it does not have a finite objective value. Therefore, strong duality simply says that the dual is either unbounded or infeasible. It doesn't say anything more. It doesn't give you any more information. Dual can do whatever. So, on the other hand, this dual is always feasible. If you put y equal to 0, it always solves this equation. So the dual optimization problem is always feasible, which means the dual must be unbounded. The fact that the primal is infeasible, by duality I know that the dual can either be unbounded or infeasible, but it's always feasible, therefore the dual must be unbounded. Is this step clear? Now let me see if I can pull up that lecture note so you can see what I'm talking about. We don't want flows. We want classes. So, so this is so if you look at this is the top part is what we have used before. Primal and dual have finite solution, P is equal to D. If the primal is infeasible, so the other possibilities are primal is infeasible and dual is infeasible. Primal is infeasible and the dual is unbounded. So if the primal is infeasible, that's what we already know, then the dual can either be infeasible or it could be unbounded. This is what duality says. So if you go back and now you say, well, that my dual is definitely feasible, therefore it must be unbounded, which means that there exists some vector yi. So the super I doesn't mean the ith component of the vector I. I'm just labeling that vector y by I. Why? Because I started out with this constraint on the right hand side corresponding to the ith basis. For the ith basis, I can create a vector yi which is strictly non-negative, sorry, not strictly, which is non-negative, such that A transpose yi is equal to 0, and the ith component of the yi vector is strictly positive. Okay. So what am I doing here? So is this step clear to people, or do we go over it again? Okay. So I'm using duality, and maybe I should write this thing in two different ways. So the real dual, so here's the primal problem, which is I want to maximize 0 transpose theta such that A theta is greater than equal to, let's make our life simple. Let's call this, it doesn't really matter. Let's call it min. Doesn't make any sense. I know it doesn't make economic sense to talk about min because why would you want a minimum arbitrage opportunity? You want to maximize the thing. But anyway, here we're only talking about feasibility. Let's talk about a min. Then my dual makes perfect sense. The min, the opposite would be a max. The variables here, now this is a sensible constraint, so I end up getting y must be non-negative. Since theta is free, I end up getting that A transpose times y must be equal to the 0 vector, which is the objective here. And I want to maximize EI transpose y, which is equal to yi. Okay, so might as well, I'll just change the notes and make that min. So that's the primal dual pair that I'm talking about. I know that the primal is infeasible. Therefore, the dual is either infeasible or unbounded. I know it's always feasible because I can put y equal to 0 and that will satisfy everything. So this means that the dual is unbounded. This implies that the dual is unbounded, which means that there exists some vector yi. So yi is a vector in Rm plus 1. Is it m plus 1? Yes. So yi is a vector in Rm plus 1 such that it satisfies all the dual constraints. So yi, the vector, is greater than or equal to 0. A transpose, the vector yi, is equal to 0. And because the value of this dual is unbounded, I know I can find a yi such that its objective value, which is ei transpose yi, is strictly positive, which is the same thing as saying that the ith component of this vector is strictly positive. The dual optimization problem is unbounded. Its value is going to plus infinity. And therefore I can find some y where its value is strictly positive. If I cannot find such a y, then it means that it's bounded by 0. And therefore it cannot be an unbounded problem. So if it's an unbounded problem, I can find some y whose value is strictly positive. Just pick one of those. I don't really care what. Okay? So far so good?
The first implication, did you prove it in the course, or is it just...
Well, I don't prove it, but it's actually, if you want it, I can put a note into the lecture notes. It's actually pretty simple to prove. It doesn't really say anything. It's a meaningless statement in some sense. We proved in the course that if you look at this primal dual pair, right, we proved that this guy is going to be a lower bound on this guy. We said that the dual, if this primal is a minimization problem, therefore the dual will be a lower bound on the primal. And so all I'm saying is this, although it sounds fancy, it's really has no meaning. I mean, of course, if one is an upper bound, it can be either infeasible or unbounded, right? Okay, so far, all I've done is that for every I created a vector yi which is non-negative. So now what I create, so now what I did was I add up all those vectors. I get n plus 1 different vectors, one for every I, and I create a new vector y, which is the sum of these vectors yi, I going from 1 through m plus 1. One for every component. And now I claim that this vector y is strictly positive. Every component of this vector is strictly greater than 0. Why? Because each of these yi vectors satisfy these properties. They satisfy A transpose y equal to 0. We haven't used that yet. But they also are dual feasible, which means that yi is non-negative. And the ith component of the yi vector is positive. Added up m plus 1 of them, every component of them has to be strictly positive, and the other guys are giving non-negative contributions. Okay? And the other thing I also know, which is written wrong there, is that A transpose times y is strictly equal to 0. Why? Because, this is probably not visible, so let me write it up here. I don't need the primal dual now. So I have a vector yi, I sum them up for I going from 1 through m, call that my vector y. I know these properties. Y is strictly positive, and A transpose times y, which is nothing but sum of I going from 1 through m, A transpose times yi, that is equal to the 0 vector.
Is it m or n plus 1?
N plus 1. Sorry, n plus 1. So far, so good? Okay, we're doing good on time. So now all I'm going to do is replace back my definition of A. What was the definition of A? Remember, A matrix was S1 transpose minus S0 transpose. That was the definition of A. So what is A transpose? S1 minus S0. And what this statement says is that A transpose times y is equal to S1 minus S0 times, let's call it y1, what notation should I use? I'm just going to use the notation y1 colon m and ym plus 1. This is just coming from MATLAB notation. So I'm taking the first m components of y and calling it the y1 through m vector, and the m plus 1th component, I just took it separately. So this thing is equal to 0, which is equal to S1 times this vector y1 through m minus S0 times the vector ym plus 1.
This is when there's no arbitrage.
Everything no arbitrage. Otherwise, I can't conclude that this LP is infeasible. The only reason I can conclude this LP is infeasible is because I know there is no arbitrage. Everything that's building from there is from the basic assumption that this primal LP is infeasible. From there, everything else follows. So now I define this vector pi to be the vector y1 through m divided by the ym plus 1th component. I can do this division because I know that ym plus 1 is strictly positive. I've created a vector which was strictly positive, and therefore I can divide this. From this equation, I end up getting that S0 is equal to S1 pi. And the claim is, I'm done. Pi is the state price vector. Now let's try to figure out, why is this pi a straight price vector? Okay, so let's review the story so that it's clear to everyone, and then we'll talk about why this pi is a state price vector. What is the story that happened? We created a model for the single period market, which is defined by the prices here and a matrix of prices on the other end. There's a vector of prices here and a matrix of prices. We define two kinds of arbitrage. We recast the arbitrage in terms of this algebraic definition, and now we are assuming that there is no type A arbitrage, there is no type B arbitrage. Under those conditions, I know that this kind of an LP, no matter what value of I you stick in here, is going to be infeasible. For m plus 1, it's infeasible because there is no type A arbitrage, and for I equal to 1 through m, it's infeasible because there is no type B arbitrage. Put it all of that together, you end up getting this statement. So no arbitrage. So the conclusion that we can draw after all of that algebra is that no arbitrage of any kind implies that there exists a vector pi which now belongs to Rm, because I took the first m components and divided it by the m plus 1th component, which has the following property. Pi is strictly positive, and the price today of the n securities in the market is equal to S1 pi. All right? Okay. So is everybody with me up to this point? At which partial point did I leave you? Questions? Yes?
I didn't understand why no type A, why no type B.
Why in the market, you mean? Physically, or the assumption that I'm making?
Assumption. Like, why, if A theta is greater than or equal to En plus 1, why is it that there is no arbitrage?
Oh, okay. That part I can tell you very easily. So I thought you were asking a more basic question as why are you assuming that there is no arbitrage? Okay. So here's the story. Let's go with the word definition. Do you buy this word definition?
Yes.
Right, you're comfortable with word definition, right? Okay. So now let's start with this type A arbitrage business. So suppose there exists a type A arbitrage of some kind, right? So there exists a theta such that minus S0 transpose theta is strictly positive, and S1 transpose theta is greater than or equal to 0. Okay? Let's call this strictly positive number something, delta. So this quantity is equal to delta, which is strictly positive. Delta is some positive number. Now what do? I create a new portfolio, theta. Let's call it theta sub delta, which is nothing but 1 over delta times the old portfolio theta. Theta was free. I could do whatever I want with theta, right? Now what happens to this guy? What is its payoff? Minus S0 transpose theta delta is going to be equal to minus S0 transpose theta divided by delta, which is equal to minus 1. Or plus 1, sorry. Right? I rescale things so that its payoff is equal to 1. And that one still remains. S1 transpose theta delta is still greater than or equal to 0. That's all I cared about. I cared about that the payoff tomorrow is non-negative, and the payoff today is at least 1. And my claim is that assuming that something is strictly positive is equivalent to assuming that it's greater than or equal to 1. Because I can rescale things. Right? That's what happened here. Here I'm just saying I created this minus S0 at the bottom. I'm claiming A theta, which will give me S1 transpose theta at the top, which is non-negative. And minus, there should be a minus sign in front here, minus S0 transpose theta must be greater than or equal to 1. Okay? So regardless of whether there is a, whatever be the arbitrage, I can always make it to be greater than or equal to 1. Same argument works for type B arbitrage. Type B arbitrage says non-positive now, and at some state of the world it's at least positive. Again, use the same argument and make sure that in that state of the world the payoff is 1. Okay, just scaling. Now, why would this actually, one of the assumptions that's going on here, if you connect it back to reality, we are sufficiently far away from it right now, but if you connect it back, you end up getting this thing that all of this argument works only if there is sufficient liquidity. Because you're assuming here that I can scale up my theta. Delta could be 10 to the minus 3 or 4 or whatever. I'm assuming here that I'm scaling up my portfolio and there is enough liquidity for me to do it.
Enough liquidity so that the prices don't change.
Prices don't change, everything remains constant. So scaling things is not going to affect the market. Right? So that part explains why I ended up getting this algebra for no arbitrage. Any other questions?
Theta is for Fourier. What does it mean? Is it a vector or?
Yes, it's a vector. So earlier we had 3 different vectors, theta 1, theta 2, theta 3, the number of assets that I have. So earlier when I was showing you an example, in this case theta would have 3 components, theta 1, theta 2, theta 3. 3 assets, 3 positions. It is not normalized, it's just the positions in those assets. So once you buy this algebraic definition of no arbitrage and you assume that the market has no arbitrage, why do we assume that the market has no arbitrage?
Because the trading has eliminated discrepancy.
Yes. So if there exists one, there are enough number of intelligent people willing to kill it. Yes.
We basically have m plus 1 different LPs, right?
Correct. We have m plus 1 different LPs for each different value of I. So for each value of I, each EI, I create an LP. All of them are infeasible. All of them are infeasible. So all of them give me for each value of I end up getting a vector yi, which has this property that the ith component of that vector is positive. And since I have these m plus 1 LPs, I solve all of them. I end up getting m plus 1 vector, each of which has the ith component positive. Add them up, I get a vector which is strictly positive on all components. Clear so far? 3 more minutes. No. Okay, so now I'll let Ali also take some of my pain away from me by explaining it some more. But, so far all we have done is we figured out this statement that, let's just expand out what does this mean. S0 is equal to S1 pi. This is what we have at the end of the day. Let's just expand out what this means. It means I'm going to replace the value of S1, which is S of omega 1, S of omega 2, S of omega m, times this vector pi, which has components pi 1, pi 2, pi m. Just expanded out the definition. It simply means that pi 1 times S1 omega, S of omega 1 plus pi 2 times S of omega 2 plus so on pi m times S of omega m is equal to the S0 vector.
When you say pi greater than 0, does that mean?
Component wise. Each component of y is positive. So whenever in this course I talk about a vector being greater than 0 or greater than equal to 0, it means component wise. Otherwise it doesn't have any other meaning. So this is what it means to multiply this and set it up. So what this basically means is that the price of each of the n assets today is given by, so let's take an ith asset. The ith asset, here it says S0 of I, the ith component, is equal to pi 1 times the ith component in state 1 plus pi 2 times the ith component in state 2 plus so on pi m times the ith component in state m. So it means that the vector pi prices each of the n securities correctly. The price today is equal to the price tomorrow multiplied by the state prices, or the payoffs tomorrow multiplied by the state prices. For the assets that I began with n securities whose prices were given to me and whose prices tomorrow were also given to you, or payoffs tomorrow were also given to me. And at the end of the day, using this whole complicated LP story, I ended up showing to you that there exists a single vector pi which prices all the n assets correctly.
How come this pi is single?
What do you mean by single?
I thought it was not a unique one.
Nobody said they is unique. There's a single meaning that it doesn't depend on the asset. There's a fixed pi that prices all the assets correctly. There could be multiple pi that price the same assets correctly, but the pi does not have to depend on the asset. It's independent of the assets. Now the question is that is it true that for every x which can be written as S transpose theta, the price of x today must equal sum of I going from 1 through m of pi I xi? This is what the definition of state price deflator was. Now we want to prove that any x which has that property, I should be able to write it as that price. So what would we do? Yeah?
Just to collect the transpose of the expression and divide by theta, we find
Take the transpose of what?
the first expression.
This one? Yeah? And then what do? So you have S0 transpose is equal to pi transpose S1 transpose, and then what do I do? Multiply by theta, and I end up getting pi transpose x on this side. This is what is on the left hand side. Now I need to make one more little jump to say that this price must equal the price of that portfolio. And what is that jump? You're absolutely right. So far it's been correct. But the next step that I want to say is, why is